invitation. Can you hear me? Great.
Thank you.
Is the sound good? You can hear me?
Yes, it's perfect. Thank you.
Perfect. Okay. Well, thank you so much for inviting me to give a talk. Today, I'm going to talk about various different projects. Some of them are taking place in my lab. But let me first start by saying that many of you know that we've seen a lot of impact of machine learning and deep learning in particular in spaces like speech recognition, vision, recommendation engines, language understanding, and even in places like drug discovery and medical image analysis. And what is it that we want to do? Well, ultimately, we want to be able to develop algorithms that can see and recognize objects around us, that can understand human speech, that can reason and understand natural language, that can move around autonomously, explore or plan, and in general display human-like intelligence. Now, if you look at some of the challenges, there's a lot of work in machine learning and AI and deep learning. And I think that, I sort of list a few of these challenges. I think from my perspective, I think that natural language understanding and reasoning remains one of the key challenges that a lot of people in our field are working on. Also in the space, what's called embodied AI, where you're building agents that can explore and actively move around the environment, and this sort of falls under the umbrella of deep reinforcement learning and control. There is also a lot of interesting work in trying to figure out how can we incorporate structured domain knowledge into these complex systems. So we'll talk about that today as well. And also, how do we deal with multimodal data? So for example, getting language and vision. How do we learn in a semi-supervised setting where you have a few labeled examples? So self-supervised learning, where you're trying to design your own task so that the agent can learn on their own without actually needing additional supervision. So in today's talk, I'm going to highlight multiple of these research directions. So let's look at first at natural language understanding and reasoning. How can we incorporate structured domain knowledge? So if we think about deep neural networks, we typically think about inputs and outputs. So for example, given an image, you're trying to predict the label for that image. Or given in machine translation, in neural machine translation, given an English sentence, you're trying to output the French sentence, right? But then if I ask you the question of, which coronaviruses are known to infect people, there are multiple answers. And obviously, we need to perhaps use some form of domain knowledge, right? So, for example, because how do we going to get the answer to that question? Well, there's a lot of work trying to look at the language understanding from what's called unstructured data. So think of this as Wikipedia articles or news articles or any sort of free-form text. But also, can we integrate, for example, more structured knowledge like knowledge bases or ontologies, or even data that comes to us from the tables, or something that's more structured. And the question is, how can we deal with data that's heterogeneous, right? That's coming in a free text, perhaps as a knowledge base in other form. How can we do some form of reasoning, meaning that we kind of like need to understand where these different sources of data are coming from and how to get the correct data. And also, how can we do it under what's called weak supervision? So for example, here to answer this question, typically, you're going to have at the training time, you're going to have a question and you're going to have the answers. But actually, labeling exactly which sentence and what Wikipedia article, is relevant and which part of your knowledge base is relevant, labeling this entire sort of reasoning step is very labor intensive, right? So it's very difficult to do. So how can we do it without actually going through that, through those stages? And one of the things that, a lot of times when people effectively look at even question answering systems is building what's called knowledge bases. So for example, you can go through the text, unstructured text, you can try to find important concepts. So for example, if you're building a medical database, these are the things you would extract. And then you can extract relations. These are facts about those entities. So for example, here you could extract that, diabetes is an instance of a disease, or diabetes can be treated by, specific drug and so forth, right? So if you build this knowledge base, then in principle, that summarizes information that you have, right? And that sort of, you can think of this as building a prior domain knowledge, right? And typically, a lot of the knowledge bases like this are built by humans by labeling and going through a lot of annotations. And even if you look at big companies like Google and Facebook and others, a lot of what they do when you type in the query is they actually have these large-scale knowledge graphs, right? That try to understand relationship between entities. And obviously, if you ask a complex question, if you can map this question to these entities and relations, then you can answer those questions, right? But now, one thing that you can do is you can say, well, if I have a question, what you can do is you can do some form of text retrieval. So for example, if you're looking at 50 million passages and 50 million entities, the graph contains 50 million entities, you can try to retrieve a subgraph of, let's say, 500 entities and 50 paragraphs. And then you can use deep learning or graph neural networks to do a form of understanding of how to sort of, how to fuse the information together, coming from unstructured data as well as structured data. So you can think of this as, sometimes your knowledge graphs are incomplete or they can be noisy. Getting them, labeling them is fairly expensive. On the other hand, getting the free-form text is actually cheap. You can just go on the web and go through the news articles or go through the Wikipedia articles and just use that to answer, let's say, question. But obviously, by combining both sources of data, you can actually improve the quality of the answers and the quality of understanding. And the question is, how do you fuse these two different sources of data together? So one of the ways that you can do it is you can build what we call text-augmented knowledge graphs. So we're trying to use information from both sources. So let's say if I ask you the question, who voices the dog in a Family Guy? And Family Guy is a cartoon show. You can basically perhaps figure out the path through your knowledge graph and unstructured data. So you can say, well, there's a Family Guy. It occurs in this sentence, so that links Family Guy to the dog named Brian, and then you can kind of extract what the right answer is, right? So you can think of it as kind of fusing different pieces together. And how we do this? Well, we actually do it as follows. We can say, well, given the question, we're going to be using recurrent neural network to get the representation of the question. And more recently, you can use transformer architectures or any large-scale pre-trained neural language models. You get the representation. And then here, you're also going to be linking entities to their appearances in text, right? So for example, this particular entity occurs in this text and this entity occurs in this text. So you're building a bipartite graph. And through the use of graph neural network, you can propagate information and update the nodes in your knowledge graph, as well as update representations that you're getting from recurrent neural networks, and passing it through the graph neural network to get updated representations of these entities that you have in your knowledge graph. And then you're doing standard sort of cosine similarity or dot product between these representations, and you pick the top, the one that scores the top. And you can train this entire system in a gradient-based manner, so you can backpropagate gradients by optimizing this objective, right? But the important thing that I wanted to communicate here is by using graph neural network, you can actually propagate information from your knowledge graph to the unstructured text, and from unstructured text back to the knowledge graph. Now, just to give you an intuition of what the graph neural networks are doing, so imagine that given a particular graph, let's say with nodes and with vertices and edges. So again, vertices can represent entities, think of them as nouns, and edges would represent relations between those entities. And given a natural language question Q, which contains a bunch of words, we're essentially going to be learning a function f, where the output of this function is 0, 1, and it's 1 if and only if this particular node is the answer to the question Q, right? And so you can formulate this problem by saying, well, the probability that this is the correct answer, so a particular node is the correct answer, is going to be given by the softmax function, and HQ is going to be the representation of the question that you get through recurrent nets or through transformer architectures, and HV is going to be the representation that you get from a graph convolutional neural network. And that's where you're fusing together the knowledge graph with unstructured data. And if you look at what the graph neural networks are doing, it's actually fairly simple. Graph neural networks are essentially instances of, you can think of them as instances of recurrent neural networks, with one caveat that, the information propagation happens with respect to the structure of your graph. So for example, if you're updating this red node, you're basically collecting information from the neighboring nodes and you're updating this red node. And then once the information in the red node is updated, it propagates out to the outgoing nodes. And so here it's sort of, the representation that you get in the hidden state is given by whatever representation you had at the previous time step, plus all the information that you could get from the neighboring nodes. And you sort of repeat this process, a few steps. And so the way that information flows between unstructured data and structured data is this way. So for example, if we get some representation of, let's say, a node in your knowledge graph, then when you're using LSTMs to get the representation, let's say, of this sentence, you can augment that representation with the representation that's coming from the knowledge graph. So effectively now, if you ever work with language models, you would typically say, well, I'm going to be using BERT-like embeddings, for example. I'm going to be using recurrent neural networks to get an embedding. What this is doing is this is saying, I'm going to get the representation of the sentence, plus I'm going to augment it with the representation that's coming from my knowledge graph, right? And the other way around, if you're updating representation of your knowledge graph, the node in your knowledge graph, then when you're doing graph convolution, you can actually augment this representation with the representation that's coming from this specific sentence. So this is part of the graph neural network, plus this is the representation that you're getting from a sentence. So these are sentences all containing this particular entity. So essentially enhancing your knowledge graph representation with the data that's coming in the form of text. And so in this case, what we find is that if you look at knowledge bases, which is the standard way of answering questions, and if you look at the notion of completeness of 50% complete, basically means that we take our knowledge base and we only retain 50% of the entities, right? Or we only retain 10% of the entities. So you can see that as your knowledge base becomes smaller and smaller, not as complete, then you're not answering as many questions. And then here you can sort of see that if you're using this fusion of graph neural networks, knowledge bases, together with textual representation, you can actually do much better in these different tasks. Okay, so that's one kind of takeaway message, is to say, well, instead of using black box deep learning models, if we actually augment them with representations that's coming from the knowledge base, we can actually do better. Now, when we think about this entire pipeline, there is also an interesting aspect of what we call multi-hop questions. So what's the idea here? So imagine that I ask you the following question. Where is the company which manufactures voglibos, which is a specific type of a drug, headquartered? Okay, so how do you answer a question like this? And in fact, a lot of existing systems, like Siri or Google and such, they do have a hard time figuring those questions out. And the reason why those questions are difficult is because you need to answer two questions effectively. You need to figure out which company manufactures a specific drug, and then you need to figure out where it's headquartered, right? And what's interesting is that, let's say you figure out you want to answer this question, and you need to retrieve, the answer to that question. So here you can, if you find the answer would be, it's a product of Takeda Pharmaceutical Company. Now, once you know what what this is, you can then retrieve another passage that says that this pharmaceutical company is located in Osaka. So the answer is going to be Osaka. Right? Now, what's interesting about these types of questions is that this representation is unknown. When you're asking this question, you're not parsing this question into two sub-questions and you're separately solving them. You're answering those questions separately, right? So you need to be able to design a system that understands that it needs to do these two steps in this case. And you can think of this as a basic form of reasoning, right? Because you really need to, from this language, which is natural language, you need to understand what these two pieces are, and you need to be able to retrieve two different sources of data to be able to answer this question. And what's even more interesting is that you cannot answer the second question before you answer the first question, right? So you can't sort of treat it as a monolithic process. It has to be kind of a sequential process, right? And so this is where we can inject domain knowledge or prior knowledge by knowing that there's notion of sequential, step here, which, in a standard deep learning models would be difficult to do. So how are we going to do this? Well, there's some prior work that sort of attack this problem, but the question is, can we do it in an end-to-end fashion, meaning that we can train the entire system from the beginning to the end using gradient-based optimization? Can we do it efficiently? And can we do it compositionally? So we can structure, let's say, if we answer 2-hop question, we can answer 3-hop question and so forth, right? So we can answer more complex questions. And so, here's a system that we've built. This was done jointly with Google. So here, just to show you, the question is, which company founded by Steve Jobs was based in Redwood City? And just to show you, this is done on a single desktop, a single GPU. And here you're analyzing 5 million Wikipedia articles, and that's done in real time. So you're analyzing 5 million Wikipedia articles, and then the answer that the model comes up is next. And these are the top 2 retrieved most important sentences, what we call mentions. So here, this sentence says Jobs was, CEO of Apple, and then he also was a co-founder of a company called Next, right? So that's a very relevant piece. And then the second important piece it retrieves, it says Next is the company, that was based in Redwood City, California, right? So you have this piece of evidence. And you combine those 2 sentences together, and then it's very easy to answer that the right answer here is the company called Next. And these are sort of, the top ranked retrieved representations, or retrieved sort of sentences that are relevant for answering this question. Right, so the question is, how do we do this? Of course, it doesn't work all the time. There are cases where the model will fail, but a lot of times it actually does find relevant pieces of information and fuses those 2 pieces together. Okay, so let me go through the stages of how we actually build a model like this. So one of the things that we do is we do what's called relation follow. And the idea here is this follows. Let's say if I have a particular R, so if I have a particular entity X, right? Well, think of this, in this case, it's a name of the drug. Then I can follow relation R in order to arrive to a new set of entities Y. Right, so it's kind of this sequential notion. Given X, I follow relation R, and then I arrive to the new set of entities. And I can repeat this process twice, for example, to answer 2-hop questions. So I can repeat this process 3 times to answer 3-hop questions. So for example, in this particular setting, X would be the Logwibals, which is the name of the drug. R1 would be manufacturer, who's the manufacturer of this drug. And R2 would be the headquarter location, right? So if you can parse the natural language question into these pieces, then you can construct a deep learning model that sort of follows this structure, which is given X and relation R, give me the set of answers. And now given the set of answers, follow relation 2 to arrive to the final set of answers, right? And so each block here is going to be modeled by a transformer architecture, but you can see that we're stacking them together in a very specific way. So let's look at one block and let's see how we're doing this. Let's say we have some text corpus. So think of text corpus as containing what we call mentions. Think of them as sentences. In our case, mentions are basically sentences. So we have on the order of, I can't remember, but they get in the order of like 1 billion sentences. I think we take the entire Wikipedia and just look at every single sentence in the Wikipedia. And then we also have entities. Think of entities as nouns or short kind of, combination of two nouns, right? So there's a way of extracting these entities, and we also have on the order of 1 billion entities, right? So think of this as sort of every single noun you can think of. And then you can construct this large-scale bipartite sparse graph that basically says this entity occurs in this sentence and this sentence. This entity occurs in this sentence and this sentence. And this entity occurs. So it's just a large-scale bipartite graph, right? That links entities to the sentences, right? And now what we can do is we can say, well, given X, particular entity, and a given particular relation, what you can do is you first can expand X to co-occurring mentions. So for example, you can say, well, this X occurs in the following million sentences, or in our case, I think we restrict to the order of 100,000 sentences, right? So it occurs in all of these sentences. Then we're going to filter those sentences or those mentions based on the relation. So for example, in this case, this relation holds. This doesn't hold because it doesn't talk about this relation, and this doesn't hold because it doesn't hold about this relation, right? It doesn't talk about the dog in the show. So we filter those out, and this is where learning happens. And then we're basically combining the scores of the same entity. So for example, this entity gets the score from here and gets nothing from here. This entity doesn't get anything because it got filtered out. And then we basically just looking at the score here. And the key idea here is that we can do all of these operations efficiently with inner products, right? So let's see how we actually do. And that's what allows us to build these systems, and that's what allows us to build systems that work really fast, right? Because essentially the entire operations is just embeddings and operating on those embeddings using dot products. And of course, how we construct those embeddings is in a specific sequential structure that we're using becomes very important. So let's see how we do it. Let me quickly look at all of those 3 steps. So let's say the first step is actually fairly simple. Let's say you have an entity family guy. So you encode it as a 1 of k encoding, vector of 0 and 1. So it's 1 in one location, 0 everywhere else. You're multiplying by the matrix A, which is pre-computed, which is this bipartite matrix. It's essentially telling you just converts an entity into the set of sentences. It's telling us that this entity occurs in these sentences, right? So it's sort of, and it gives us, particular mentions or sentences where it occurs. So this is just a simple matrix. We pre-computed beforehand, and we just do the mapping. Then we're going to filter those mentions based on relations. So let's say we have a particular relation. This is where the query comes in. We encode this query using transformer models, right? And we also encode every single sentence using large-scale pre-trained language models, right? And then we do the inner dot product between the two, right? So this is telling us, is this particular sentence consistent with this particular relation? And again, we can fine tune the parameters of this model at the training time, because at the training time, we know the right answer. So we can fine tune this model. And effectively, and this is using, I think in our case, we're using BERT-like embeddings. And so the way that we actually do it is we build this large scale of what we call offline index. Every single sentence in Wikipedia gets transformed into a 100-dimensional vector. It's a dense vector, and we just store it. So we can effectively store the entire Wikipedia on a single machine, just in terms of these dense embeddings, right? And then what we can do is we can essentially look at the top k nearest neighbor, which is very fast, to filter out which sentences correspond to a particular relation, right? And then once we do this filtering, then we arrive at a set of sentences or a set of mentions that are consistent with this relation, right? So essentially that's the filtering step. And the way we're optimizing for this model is we can look at, at the training time, we know what the right relationship is, we know what the right answer is. So we can actually fine tune the model to optimize for retrieval of correct top K neighbors. And once we do that, we do element-wise product, and then now which basically we arrive at the sentences or mentions which satisfy this relation. All right. And once we have these mentions that satisfy this relation, we multiply it by matrix B, which is the transpose of matrix A, which maps the mentions back into the entities, right? And once we have these entities, then we essentially, once we have these entities, then we pick the top scoring one. And that's that's giving us the answer. And so if you look at the entire operation, right, we sort of have these pieces where we take the mentions, entities, we transform into mentions, we do the retrieval, we transform them back. And that's sort of this operation of relationship following, right? So we're expanding it, we're filtering it, we're combining the scores for the same entity to sort of get the answer. And it's efficient. It's closed under composition. So that's how we sort of do. We combine both of these operations. So we can stick these operations together to answer, let's say, 2-hop questions. And the entire thing is differentiable because we can backpropagate gradients through these operations. So if we need to fine-tune parameters of how we're doing retrieval or parameters of our language models, we can actually do the fine-tuning. So entire system can be built in an end-to-end fashion, right? And the way that we actually implement this is we, to get the X, we do soft entity linking. Then to get the relation 1, we're using transformer architecture, and R2 to get the transformer. So the important thing I want to emphasize here is that we have these little modules, and these little modules, operate on enforcing this particular structure. Now, one caveat of this architecture is that, we're only answering this follow relationship. Now, there are some questions that, require us to answer questions that can be, not the follow relation, but other forms, right? Like, for example, intersection of the two answers, of the two sub-questions, or a union of the two and stuff like that. So that requires us to start, thinking about, more generic architectures that can do that. Right? And again, the entire system can be trained in an end-to-end fashion. And if we look at sort of performance of these models, right? For 1-hop questions is about the same. Once we start looking at 2-hop questions, these graph neural networks and our model, we actually do better. And in 3-hop questions, we can even do better just because we're putting that specific structure in place. But what's interesting is that we can also do it very efficiently because we represent all sentences or mentions in this large-scale offline index, right? So it sort of allows us to build. So here we can answer these complex questions. I think we can answer 19 questions in 1 second, right? So speed also becomes very important. And ultimately, when you think about these systems, how do we represent common sense knowledge? How do we do this sort of form of reasoning? If we think about human knowledge is abstract. It's built on high-level concepts. So one example I typically give is that, let's say you have a dog. The dog has 4 legs, right? And so as a human, when you're looking at this image, you can sort of recognize it as a dog because, you know that dogs have 4 legs, and this looks like a dog. Now, if I take this image and I put, 4 more legs, and so it's going to be dog with 8 legs, let's say, right? As a human, you would look at this image and you would say, I don't know what this is. It looks like a dog, but probably not. A lot of existing deep learning systems and, based on convolutional neural networks, what they will do is they would say, yeah, it's a dog because it contains all the different features of a dog. As long as I find sufficient number of features, as soon as I do sort of pattern matching on some number of features, then I can confidently say it's a dog, right? And so a lot of existing systems would fail precisely because they can't encode these sort of abstract knowledge, or they require a lot of training examples. For example, if you give it many images of dogs with 8 legs and you call it something else, then the model would learn that, right? But on its own, it can't. And so how do we encode this knowledge and how do we do it efficiently is still, one big area of research. So that's why it's very easy to fool these models. And it's very easy to fool the models that are, question answering models as well by, manipulating a little bit of a text and the model would, completely fall apart. So, this sort of gives us the notion of, language understanding. But let me also talk a little bit about embodied AI, reinforcement learning, and then I'll show you how we can combine language understanding with the reinforcement learning as well. So let's look at deep reinforcement learning and control, and in particular, a space of what's called embodied AI. And a lot of this work was done by my student, Devendra Chaplot. So when we think about reinforcement learning, we typically think about learning behaviors. So we want to learn sequence of observations to actions, right? And in order to achieve a specific goal. So for example, if we think about physical intelligence, think about physical robot. You have an agent, you have an environment. The agent observes the environment. So let's say it sees that particular image, it takes an action. Let's say the agent says, okay, go forward, turn left, or takes any other action. And if you think about, an actual robot in the environment, agents, they need to move around the world. If you take an action, it will impact your future observations. So whatever actions you take will impact what you see next. So in some sense, you can think of it as, you're operating in an active setting. And it requires some spatial and semantic understanding of the environment, right? So let's focus on one specific task, which is navigation, right? So the specific task of, in the context of embodied AI, there are multiple tasks, but let's think about navigation. So let's say, you given the observation, you take an action, you get some reward. And if you've reached your action, if you reached your goal, you get positive reward, otherwise you get negative reward. You can think about, when people talk about end-to-end reinforcement learning or black box reinforcement learning systems, they typically think about, given an input, you pass it through the deep neural network. The deep neural network outputs an action. Sometimes you get positive reward, sometimes you get negative reward, and then gives the signal for training parameters of this neural network. Right? And this is sometimes called policy because the policy is the mapping of your states and what you observe to the set of actions. Now, let's look at the goal condition navigation. So in this setting, I actually tell you where you need to go. I give you the goal, and you need to figure out how to get there. So for example, the goal could be a point goal. I give you X, Y coordinates. There's a lot of work in image goal navigation. I show you an image of a TV and tell you, find me where my TV is. There's an object goal where I specify, let's say, get to the TV. And then there's also language goal. I think of it language instructions, where I tell you what you need to do, and then your agent goes and executes it. And I'm going to show you at the very end, like, one of these examples. And language goals are actually useful because they're convenient for humans to interact with your agents, and they also have this notion of compositionality, right? So you can compose, you can give them instructions. For example, you have, you can learn compositionally. So one of the key challenges when we think about these systems is exploration, being able to move around the environment and learn about the environment, right? So let me show you one example. This is the system that we built at CMU. And this is, here the agent moves around in this virtual environment. These are reconstructions. And it sort of moves around the environment. And now here you actually have a physical robot. You're transferring whatever you've learned onto the physical robot. And this physical robot moves around and actually explores the environment. Right? So it moves around and tries to understand, where the objects are, how they're located, where the obstacles are, where the free space is. And it's trying to understand the layout of the rooms and actually build what we call the semantic map of the world, right? And by doing that, then we can give our agent a specific goal. So for example, here we're going to give it a goal to find a potted plant. So here you see it's trying to find a potted plant, and as it moves around, it builds the semantic map of the world. It understands, it's trying to figure out where the couches are, where the table is, and so forth, up until it figures out where the plant is, right? and sort of has to, and so there are multiple pieces involved. You have to have a visual understanding piece, you have to have reinforcement learning aspect of it, and such. Right, and even beyond that, when we build these agents, how do we get semantic price and how do we get the common sense into these agents? So for example, let's say you have an agent, and let's say this is the image that you're trying to reach, and you're considering 3 paths, right? Path number 1, path number 2, and path number 3. And the question is, which path would you take? And as as a human, you would basically say, well, stoves are located in kitchens, and kitchens are typically on the first floor. So I would probably choose path number 1 or path number 2, probably path number 2, right? Because it looks like it's going to go into the kitchen. But you would never consider path number 3, right? You would never consider going upstairs because kitchens typically are not upstairs, right? It's like, if you have a friend in your house and your friend says, well, can I grab a glass of water? And you say, yeah, of course, go grab a glass of water. And your friend kind of like goes upstairs and starts looking for the glass of water in your bedroom and, all over the place. Then you'll basically say, what are you doing? Right? And we sort of use this semantic price and common sense to move around the environment, not just in navigation, but in other tasks as well. But most navigation algorithms basically don't do that, because to the agent, all of these settings are unexplored, and so they're likely equally probable to contain that particular image. So you need to have some sort of semantic understanding of the notion of that this is a stove. Stoves are located in the kitchens. Kitchens are typically on the first floor, right? And so the question: how do you encode that knowledge? How do you learn that knowledge? Right. Now, let me show you one instance of how we basically going to try, not necessarily solve this task, it's a very difficult task, but how we can try to build an agent that learns on its own by exploring environment. So when you think about internet versus what we call embodied data, these on the top row, you see static internet data. So this is the data where people take pictures and then they label. Right, so there's a lot of data sets typically used in computer vision for semantic segmentation and so forth. Below, you're actually seeing embodied data, active embodied data. So this is the agent. There's a lot of consistency in the environment. It's kind of very sequential, obviously. And sometimes you see images like this, where there's like a big doors and there's like little things that you're seeing here, which typically you don't have in the internet data, because people wouldn't take images like this. Right? Like, why would you take an image where you have like a big gigantic doors and you don't really see the rest of it? Right? And so the distribution of images that the robot sees versus what you see on the internet is very different. But what we do right now is we actually train our models on these images because these are labeled for us. And then we use these models, these detection, semantic segmentation models, and sticking them into our agents, because that's the best thing we can do. And so the question is, can you actually build a system that improves on these sets of images by exploring the environment? Okay? And so again, sort of like to show you an example, if you take the best state-of-the-art internet-based model, then you can get a false positive. So here it thinks it's a chair, right? Or you can, you're trying to find a toilet and you're missing it, because it's partially occluded. Right, so there's no images on the internet that sort of like have partially occluded object and then you labeling that, right? Typically, people don't take images like this, and so you get another false positive. And so when you think about active embodied data, there is a notion of consistency, right? Consistency of objects through time, and this is not new. People have known about this. As your agent moves around, the same couch persists. It's not like on this frame, this couch disappears, on this frame, it appears again. Right? So these are not independent sort of instances of images, and this notion of persistency through time and what we call 3D label propagation will allow us to improve our perception models in self-supervised way, right? By propagating labels. So if we know that label is here, we can essentially propagate label forward and create more and more training examples for our perception system. And so this comes to the notion of what we call perception action loop. And there's a lot of work with people trying to build systems like this as well. And so here, what we're going to do in the perception stage, we're going to build a self-supervised exploration model. So you think of the agent exploring the environment in a self-supervised way. And then in the second phase, we're going to do self-supervised visual learning. By exploring the environment and understanding what the environment is, we can create new training examples for our system. And our system can fine-tune or adapt or learn a perception model better. So it's kind of like in this situation, you can think of it as you have a robot, you put it in your house, and the robot just kind of moves around your house, does its own thing for a couple of days, or maybe for a day. And by doing that, it's going to improve its own perception system. It's going to improve its own object detection, object recognition system on its own. Right? Because ultimately, that's what you'd like to have in your agent. The agent that learns on its own in a self-supervised way without requiring you specifying additional labels. So how do we do this? So at the first step, we're going to do the following. We're going to get the observation. Right? This is what the agent sees. We're going to pass it through the state-of-the-art perception model, Mars-CNN model. That's trained on internet data. So it's not perfect, but at least it gives us the initial pre-trained model. Based on that, we're going to build a 3D semantic map of the world. So we're going to build a 3D representation of the world. And the way we're going to build this 3D representation of the world is using reinforcement learning and using a specific type of exploration policy. Okay. So the first step is to understand the setting. The second stage, what we're going to do is we're going to collect the sample trajectories from this stage, right? And then through the 3D semantic mapping, we're going to generate specific labels. We're going to generate augmented labels. So think of them as so the persistency labels. And then given those labels, we can actually fine-tune our perception model. And so very quickly, and both phases do not require any labeled information. So how do we do this? So this is how the agent builds, this is how the agent builds the 3D semantic map. I wish it's, 1 second, I think that my computer is frozen. Let me just show you again. Yes. So as the agent moves around, it sort of estimates the depth. It figures out where the objects are, and it's trying to reconstruct the 3D representation of the world. Okay? So these are kind of like voxelized based representation. Okay, now how do we build the policy? How do we get our agents to move around and build a map like this? The way that we do this is we say, well, what we're going to do is we're going to take our 3D semantic map. We're going to count the number of voxels that we confidently predict with probability more than 90% confidence. And we're going to sum them up. And that now becomes our reward. So we're basically going to be trained to maximize the policy that explores the environment such that it's gaining definitive knowledge as much as possible. All right. So if the agent just moves around here, doesn't do anything, and just moves around in circles, the reward is going to be very small. Oops. But if it's kind of, if it moves around the environment and identifies a lot of these different pieces, then we get a good policy. Okay, so that's the first step. The second step is to do perception. So let's say we have this 3D map, and let's say the agent is located here, and that's what it's looking at. Well, we can obtain instance level segmentations by projecting this 3D map through ray tracing back into the image space. So we can project these objects that the agent sees back into the image space. And now these become now self-supervised labels, right? Which is pretty cool because we know these labels exist there, these objects exist there, right? Now, if you look at the Mars-CNN prediction for that exact image, it's making these mistakes. It's basically not identifying this as a couch, and it's not identifying this as a chair. So these are false negatives. So now we've created additional labeled examples, and that's exactly done by constructing this 3D semantic map and knowing that these objects are static, right? Now, if you have dynamic objects, this becomes more challenging, but for static objects, they're just not going to disappear. And by using that, we can actually build, as the agent moves around in the world, we can, here's a false positive, right? We can collect we can collect the data here and improve our perception model, right? Which is pretty cool. And so in terms of the results, you can sort of see if you take state-of-the-art models for object detection and segmentation with different environments that we're looking at, a lot of existing algorithms, they basically improve only by a little. And our method allows us to improve our perception model, fairly substantially. We're still far away from completely solving the problem, but the numbers goes from here to here without any additional labeled information, just by building the 3D semantic maps and kind of like understanding the notion of consistency through time, persistence of objects, right? And to conclude, once you kind of build these semantic maps, you can also do more challenging things. Like, for example, you can build an agent that follows instructions. So here, let's say I have an agent and I give it instruction, place a cold lettuce slice in a wastebasket. And so what the agent needs to do, the agent needs to pick up the knife, slice the lettuce, put the knife and so forth, and then take the slice, put it in the fridge, and so forth, and up until, you put it into the garbage can. And this is an environment called Alfred environment. It's a very challenging environment because you need to execute these instructions. And what's even more challenging is that you're asking a system to place a cold lettuce. And if it's a cold lettuce, then you kind of like have to put it in the fridge, right, to make it cold. And then you take it out of the fridge and you're throwing it out. It's kind of a silly instruction, but at the same time, you have to have some notion of semantic understanding, right? So that the lettuce slice has to be cold. So once you cut it, you put it in the fridge. Or you take the entire, lettuce in the fridge and then you slice it. So and so here's how, what the environment would look like. So here's the agent navigating in this virtual world, picks up the knife, slices the lettuce, and does a lot of different things, places it in the fridge and so forth. And so you can kind of sort of see that there's multiple sub goals that you need to execute, and then it becomes success. And so if you think about these environments, these are the environments where you have instructions. You pass it through the language parsing model that identifies different subtasks that it needs to execute. You have an image, just the RGB image. You need to build a form of semantic mapping, understanding where objects are, what the map of the world is. And those two things go in what we call semantic search policy, that's trying to figure out what the next step should be, how you should complete the goal. And then you actually have a deterministic policy that actually executes a low-level action, like go 30 centimeters forward or turn 90 degrees left and so forth. So it's a low execution of low-level actions. So you go from high-level instruction and RGB images into these like precise, low-level instruction execution of actions. And by building these semantic maps and understanding the language part, you can actually build fairly accurate systems. So this system right now achieves about 24% accuracy. Humans achieve about 98% accuracy, so that we're still far away from the human performance. But if you look at the best sort of end-to-end reinforcement learning system, these models achieve about 8%. So by building these modular systems, you go from 8% to 24% accuracy. But we still have, a lot of legroom to close the gap between what machines can do versus what humans are doing. And again, just to emphasize, there's lots of different components here. There is a visual understanding, depth estimation, building the semantic map of the world. There is a language component, understanding what the instruction is and how to break it down into sequence of subtasks. And then everything gets put together into the agent that actually has to execute low-level instructions, like the actual physical system that has to move around in the world and execute low-level instructions. So there's a lot of different kind of like pipeline pieces that you need to build to build something like this. And so, oops. And just to finish up, there's a lot of work on trying to, go from simulation to the real world. I've shown you an example of building a system that, trained in a simulation and then get deployed in the real world. How do we do this? You know, there's a lot of work in trying to close the physical domain gap, visual domain gap, because the images might look different from, you know, simulators to the real world, and such. And we've been looking at this little Locobot robot. And so let me just finish by saying that, you know, ultimately we want to be able to build AI, and AI is going to be a lot of different challenges. You know, part of the challenge is to build autonomous systems that can move around, explore, plan, that can understand multimodal input, that can understand human speech, that can understand natural language, and, you know, interact with humans. So there's a lot of kind of, you know, interesting research that needs to be done in this space. And on that note, I'll finish, and I want to thank all of my students, because it's their work. Various aspects of language understanding, reinforcement learning, visual understanding, self-supervised learning, and so forth. So on that note, thank you very much. And I'll go to here.
I'm sorry, actually, I was muted, but I was talking.
Okay.
Sorry, yes. Actually, I wanted to thank you for the great talk. I think it's very interesting and exciting that these methods are actually solving real world problems. So I think we have a few minutes for question and answering. I would like to start with one question. I would like to know what's your opinion on refining actually the language models with robotics. So I think in your talk, we saw that having these language models, we can have like a very good robotic system that could, you know, achieve some goals. But would it be also possible to maybe refine the language model with robotics?
Yeah, I think that's a good question. I think it's possible. I think in many cases, you know, right now, the systems that we're building, we're sort of taking language as a ground truth. Somebody gives us an instruction, and we sort of, you know, basically say, well, that's a correct instruction, and then we kind of learn the embeddings for that. But I think that what you're asking is that in principle, you can see what the agent does, and by succeeding, you can in principle go back and refine the language model, or you can refine the representation of the language model as well. So for example, because, you know, instructions are very specific. You know, they're not, you know, when you interact with the agent, it's not just a generic, you know, text. And in principle, I think that you can fine tune the model. So for example, if the agent solves the task, you can take this and you can back propagate through your system and update the representation that the language is getting. So you can fine tune the language as well. Absolutely.
Perfect, perfect. Thank you very much. This answers my question very well. Are there any more questions from the audience? Yes.
Thank you for the talk. It was very cool. I have a question. If in the graph search, if the question is flawed in the sense that the answer is not unique. For example, Steve Jobs has founded another company in Redwood. What is the outcome, the result?
So that's a very good question. So in the system right now, what we do, let me just go back real quick and I'll answer your question. So in the system that we built right now, this thing here, right? So in the system that we built right now, once you combine the scores, there's going to be multiple answers here. And what we do right now is we pick the answer with the highest score. And we basically say it's one answer. But if we pick the top two answers, it would give, you know, next, and it would say the second most probable answer is this. So, you know, in principle, you could display the top 5 answers or the top 3 answers. Right. And then if Steve Jobs, you know, founded another company that was based in Redwood City, you know, it would be picked up here as well. Now, it becomes more challenging to know exactly that there are 2 answers or 3 answers. So that becomes a little bit more challenging. So you have to train for that. Right now, we don't handle that. right? But does it make sense? Because this system actually returns a ranked list of answers. So in principle, you can display not the first, you can display the top 3, for example, and you have the confidence scores associated with that. So you can say next confidence is 0.9, the next one would be Apple, but its confidence would be 0.2, right?
Perfect, thank you. Are there more questions? If not, maybe I continue on this topic. So what would happen if we have entities which, let's say one entity, or let's say 2 names for 2 different entities, but how can we, for example, disambiguate between them? I don't know, for example, if we have next for company, but also next for giving some relations, how could we disambiguate between these two?
Yeah, that's a very good question. So it's a harder to do that, but the way that we would typically do this is that we would try to find the answer based on the context. So for example, if we talk about Next, which is a company founded by Steve Jobs, the embedding of the word next is going to be, when we do the embedding, we just don't embed next, but we embed next relative to its context. Right. So if next is used in one context versus a different context, then you would end up with 2 different embeddings. So there's a common thing, like, for example, if you look at the word bank, it could be financial bank or it could be a river bank. Right. And so the word bank itself, you don't know what that means. But if you look at the context, so when you embed the word bank, you just don't embed the word bank, you embed a little context around it. So that's the way to kind of like disambiguate.
Yeah, perfect. Thank you very much. So I would like to also invite people on Zoom. If you also have questions, please raise your hand, but also people here in person. Okay, if not, then I would like to thank you again. It was a very insightful talk. And yeah, please give an applause.
Thank you for the invitation. If you have any questions, feel free to send me an email. I'll try to answer.
Perfect. Thank you very much. Thank you.
Thank you. Bye.
Bye.